Okay. Section 3.5 is about rational functions. So a rational function is one where you have, it's in the form of a polynomial over another polynomial. All right, so we're going to be talking a lot about graphing these things. So they usually will have one or more asymptotes. All right, asymptote. It's a line which is shown in the graph as a dashed line. It's not actually points on the graph, it's more of a guideline for the graph to follow, but usually doesn't touch. Okay, so here's a couple examples. Here's an example of a common look, what a rational graph would look like with a couple of asymptotes. There's a vertical asymptote and a horizontal asymptote. And as you can see, the function graph is getting closer and closer to that without actually touching it. Okay, so there's three different types of asymptotes that we're going to talk about, which are vertical, horizontal, and slanted or oblique asymptotes. So to calculate the vertical asymptote, you will set the denominator equal to 0. So the vertical asymptote is it's a place where the function is undefined. Okay. So whatever the vertical asymptote is, it's a number that is not included in the domain of the function. Okay. It's kind of a scary image to pop on your screen, isn't it? Well, maybe it'll stick in your head. That's kind of the point. Anyway, this silly picture is to help us with horizontal asymptotes. Okay, so in order to figure out the horizontal asymptotes, we are going to compare the degree of the numerator with the degree of the denominator. So if they are the same, then your horizontal asymptote is going to be y equals a over b. If the one on the bottom is bigger, then it's going to be y equals 0. And if the one on the bottom is smaller, then there is no horizontal asymptote. And by the way, when asymptotes are lines, so whenever they ask you what is the asymptote, you're answering with the equation of a line. So if it's vertical, that's going to be x equals. If it's horizontal, that's going to be y equals. All right. And anyways, so this silly little picture right here, okay, is Bobo Botno eats DC. All right, and that is just an acronym to kind of try to help you remember. Okay, so Bobo stands for big on bottom 0. So if the bigger exponent is on the bottom, the horizontal asymptote is 0. And then Botno stands for big on top, none. So the bigger exponent is on top, then there's no horizontal asymptote. And then eats DC stands for exponents are the same, divide coefficients. Okay, so that is Bobo Botno eats DC. Okay, so hopefully that'll help you remember. Okay, and then the third type of asymptote is the slant asymptote or oblique asymptote. All right, so if you do not have a horizontal asymptote, then you might have a slanted or oblique asymptote. And to find out what that is, you will divide the numerator by the denominator. All right, and you're going to ignore the remainder and just take the quotient. Okay. And it is true that the slanted or oblique asymptote only exists if the degree of the numerator is equal to the degree of the denominator plus 1. So the one on top is only one more than the one on the bottom, basically. So there can never be both a horizontal asymptote and a slanted asymptote for the same function. Okay, so that was kind of feels like information overload, but hopefully it'll start to make more sense once we start doing our examples. All right, we have lots of examples here. So this will most likely have to be split into 2 videos because I can only do about 30 minutes per video. All right, so number 1. All right, so first we're going to find the vertical asymptote by setting the denominator equal to 0. So if x plus 9 is equal to 0, then subtract 9 from both sides. That would give you x equals -9. Oh, okay. Sorry, I thought I paused my recording. I guess I didn't. All right, so the horizontal asymptote then. All right, so the degree on the bottom would be 1 since you have an x there, and the degree on the top would be 0. So that is big on bottom. Okay, so big on bottom 0 is the horizontal asymptote. So y equals 0. Okay. All right. So because we do have the horizontal asymptote, that means there's no oblique asymptote. All right, let's see. X-intercepts, so we can figure that out by setting the numerator equal to 0. But the numerator is just -6, so -6 can never be equal to 0, so that means that there are no x-intercepts, which kind of makes sense since we have the horizontal asymptote is at y equals 0. All right, and then to find the y-intercepts, we'll just plug in 0 for x. So that would be -6 over 0 plus 9. So that equals -6 over 9. And if we reduce that, that would be equal to -2/3. Okay. All right, so I can go ahead and start putting all of this onto the graph. So my vertical asymptote is at x equals -9. So 5, 6, 7, 8, 9. There's my vertical asymptote. And then, see, I was looking for my orange highlighter that I had before. I don't know what happened to that. But anyway, so my horizontal asymptote is at 0, so that's right on top of the x-axis. Okay. Let's see. And then the only other thing I have to put on the graph right this second is the y-intercept at -2/3. So that'd be right around there. All right. Okay. So to finish the graph, so I know that my graph has to have at least one point. I know my graph has to go through that point. And then I also know that it has to follow the asymptotes. So that pretty much lets me know how to draw this part of the graph. Okay, that's one piece. Then we also have the piece that is on the other side of the vertical asymptote. All right, so remember the vertical line test. Okay, so I've got this piece, so I'm not going to have anything up here above that because then it would fail the vertical line test. But I am going to have something over here. Okay, and basically all I really need to know is that I can either have something like that up here. That's one option. Or the other option is it could be down here. All right, so those are pretty much my only two options, and I just need to figure out which one of those is the correct option. So I'll just basically do an XY table. I really just need to put one number. So I just really need to pick any value of x that's over here on this part of the domain. So any value of x that's less than -9. So we could just use -10. And then we'll just plug that in. So -6 over -10 plus 9. So that equals -6 over -1, which equals +6. All right, so if we're able to plot that point, that's great. But if not, that's okay too. The important information here to know is that this is a positive number. So it's going to be above the x-axis. Let's see, do I have room? Almost. It's like up here, basically. So, there we go. Something like that is what it would look like. All right. So, the domain is going to be everything other than the vertical asymptote, basically. It's going to be -infinity to -9, union -9 to infinity. And then the range is going to be everything other than the horizontal asymptote. So that would be from -infinity to 0, union 0 to infinity. All right. All right, so that's it for number 1. Okay, number 2. Okay. All right, let's see here. All right, vertical asymptote. So we're going to set the denominator equal to 0. So if x minus 4 is equal to 0, that means x would be equal to 4. So that's my vertical asymptote. And then in order to figure out the horizontal asymptote, we can compare the degree on the top and bottom. So there would be like invisible ones here. So the degree is the same on the top and bottom. So that would be exponents are the same, divide coefficients. Okay, so the coefficients, meaning the leading coefficients here. So that'd be 2 over 1. So for your horizontal asymptote, it would be y is equal to 2 over 1. And 2 over 1 is really just 2. So y equals 2 is the horizontal asymptote. And since the horizontal asymptote does exist, the oblique does not. And then let's look for the x-intercepts by setting the numerator equal to 0. And then solve for x. So x equals -3. And then for the y-intercept, we can just plug in 0 for x. So 2 times 0 plus 6 over 0 minus 4. So that would be 6 over -4. So that would be -3/2, which is the same thing as negative 1.5 or negative 1.5. All right, and then we'll just start putting all that on the graph. So vertical asymptote at 4. And then horizontal asymptote at 2. Let me try this. Oh yeah, that looks good. It has that, sorry, it has that screechy marker sound though. Okay. Let's see here. All right, what else we got? We got x-intercept at negative 3. We got y-intercept at negative 1.5. All right, so everything looks good. So we've got to go through those points, and we've got to follow the asymptotes. Okay. All right, so now we just need to draw the part on the other side of the vertical asymptote. So it can either be up here, or up here above the asymptote, or below the asymptote. All right, now if we were to make it below the asymptote, it would have to go through the x-axis over here. Okay, but it does not go through the x-axis over here. We already calculated the x-intercept here, and that's the only x-intercept. There's no other value of x that would make the function equal to 0. All right, so there's no x-intercept over here. Therefore, we know that it's got to be up here. All right, and that's really all we need to know. Okay, so the domain is everything other than 4. Negative infinity to 4, union 4 to infinity. And then the range is everything other than 2. So negative infinity to 2. Union 2 to infinity. All right, that's it for number 2. Okay. Number 3. All right, so find the vertical asymptote, set the denominator equal to 0. So if x minus 1 equals 0, that means x would equal 1. And then for the horizontal asymptote, we have big on top, that's botno, big on top, none. So there is no horizontal asymptote in this case. All right, so that means that we may have an oblique asymptote. So the degree of the numerator is only 1 higher than the degree on the denominator. So we should have an oblique asymptote. And we're going to calculate it by dividing the numerator by the denominator. And we can do that with synthetic division. So the opposite of negative 1 is positive 1. So positive 1 will go in the box. And then the coefficients of the numerator would be 1. And then it skips the x term, so we put a 0 for that. And then we have the 4. Bring down the 1. All right, so we can ignore the remainder. So just use the quotient part, fill in an x here. So it's going to be y equals that quotient. So it's going to be y equals x plus 1, and that is our oblique asymptote. Okay. All right, so I don't know if you're wondering how that's going to look. I'll go ahead and put it on the graph for you. We've got, so it's basically y equals mx plus b. We've got the y-intercept is 1, and then we've got the slope is also 1. So just go up 1 over 1 from there. All right, and we're going to graph it as a dashed line. You can also go down and to the left. So there's our oblique. All right, we also need to calculate the x-intercepts. So to do that, we set the numerator equal to 0. All right, so subtract 4 from both sides would give you x squared equals -4. And then you'd take the square root of both sides, which would give you x is equal to plus or minus 2i. So you can't put imaginary numbers on the graph, so there are no x-intercepts. Okay. And the reason why, if you want to know why do we always just set the numerator equal to 0, well, the reason is because I can show you real quick. So let's say if we were to set the whole function equal to 0, x squared plus 4 over x minus 1 equals 0. Okay, so that's normally what you do if you want to find the x-intercept. You just set the whole function equal to 0 and you solve for x. Well, in the case of a rational function, the very first thing you would do to solve this is to multiply both sides times the denominator. Okay, well, 0 times the denominator is still 0. That cancels out, and then you end up with x squared plus 4 equals 0. So when I'm doing rational functions, I just shortcut that first step and say I'm just going to set the numerator equal to 0. So that's why we do that. All right. Next, we need to find the y-intercept. So we'll plug in 0 for x. So that would be 0 squared plus 4 over 0 minus 1. So that's 4 over -1. So that equals -4. All right. Okay. All right, so, all right, let's go ahead and start putting everything else on the graph. Vertical asymptote at 1. All right. And then the only other thing to put on the graph is the y-intercept at -4. All right, so it's got to go through that point and it's got to follow the asymptotes, and also it has no x-intercepts, so it's not going to cross the x-axis at any point in time. All right, and we don't know exactly how this goes, you know, but I'm just gonna something like that. All right, let's see. And then so now there are some graphs that have oblique asymptotes, and they kind of go like this and like that. Okay, but this is not one of those because, as I said, there's no x-intercept. So see, if I was to do this, it would have to go through the x-axis, and it would also violate the vertical line test here. So the only other thing to do is basically just kind of, it's kind of should be kind of like a mirror image up here of that up here. Something like that. Okay. So as always, the domain is everything besides the vertical asymptote. So -infinity to 1, union 1 to infinity. And then the range, in this case, we can't really determine what the range is because, like I said, we don't really know what the maximum point of this sort of parabola looking guy is here or here. I mean, we don't really know. We can guesstimate that it's -infinity to something like maybe -3-ish. We don't really know. And then it goes up to something up there, like, I don't know, 6 or something, who knows, up to infinity. Okay, but basically we don't know. All right, so you don't really worry about that. They're not going to ask you to find the range if it's not possible to find. Okay. Alrighty. Number 4. Okay, hopefully I can get through this problem before the video cuts me off. I think I can. Okay. So to find the vertical asymptote, we set the denominator equal to 0. And in this case, that's going to require factoring. But I think this won't be too hard to factor. We know we've got to have 5x and x to get that 5x squared. And then we also have to have a 5 and a 1 to get this. Now, this is positive, which means these two signs have to be the same. And then this is negative, which tells me they would have to be two negatives. Okay. And then I'm probably going to be looking for a 25 and 1. So 5 times 5 would give me the 25. And 1 times x would give me the 1. And that would give me the negative 26 there in the middle. So 5x minus 1 equals 0. And then solve that for x. So that's going to give me 1/5. And then x equals 5. So those are my two vertical asymptotes in this case. Okay. And then for horizontal, we look at the degree of the numerator and denominator. So that would be exponents are the same, divide coefficients. So that's going to be y equals 3/5. Which means there's no oblique asymptote. So if there's a horizontal, there is not an oblique. And then let's see. So to find x-intercepts, we would have to set the numerator equal to 0. So we have 3x squared minus 6x minus 24 equals 0. All right, well, we can divide all that by 3. So that would be x squared minus 2x minus 8 equals 0. And then we could factor that. That would be x minus 4 times x plus 2. So my x-intercepts then are 4 and negative 2. All right, and then for y-intercept, we would plug in 0 for all the x's. So that's going to be 3 times 0 squared minus 6 times 0 minus 24 over 5 times 0 squared minus 26 times 0 plus 5. So that's negative 24 over 5. So that equals negative 4 4/5. Okay. Okay, well, let's put all this info on the graph. So we've got two vertical asymptotes. We have it at 1/5 and 5. Okay, then we have our horizontal asymptote at 3/5. And we have x-intercept at positive 4 and negative 2. Okay. And we have the y-intercept at negative 4 4/5. Didn't leave myself enough room for that one either. Okay. All right, then. This part is obvious because we got the points and everything. All right, now let's see. Okay, now we have 2 more sections here to deal with. So with this right here, it's not in the middle here. So, you know, I mean, some people might draw it like going like this, but I don't think that's gonna be right. If it was in the middle, maybe, but I think usually what happens here is it's gonna go something like this. And then it's going to go something like that, probably. Let's see. Now over here, there's no x-intercept, so we already know what that's going to look like. It can't go through the x-axis again, so that's just basically going to look something like that. Okay, so we can use a table to try to figure out what's going to happen here. Okay. And yeah, I just simply don't have a whole lot of room, so I'll use this. I'll just do this. All right, so what I want to do is let's just use x equals 1. Okay, that'll probably be the easiest thing to do. Now, I know you might be thinking that, hey, you're not supposed to cross the asymptote. Well, notice how I said usually doesn't cross the asymptote? Well, sometimes it does, especially when it's a horizontal asymptote, and especially when you've got 2 vertical asymptotes. It's not uncommon for it to cross the horizontal in the middle. So if x is 1, I'll plug that in here to the function. So 3 times 1 squared minus 6 times 1 minus 24 over 5 times 1 squared minus 26 times 1 plus 5. Okay, so 3 minus